Good morning, everyone. So, in the last couple of lectures, we have seen autocorrelation function, partial autocorrelation function of stationary series definition, and then the SCF, PACF of stationary series. And then we have seen a couple of examples, graphs, how they look like. And today we are going to discuss in detail some of the very important stationary and a particular non-stationary processes, and then discuss, connect whatever that you have learned so far. So let's start with a simple stationary process. This is the simplest of all, which is basically a one-step generalization from the IID series. So let xt be a series with expectation xt equal to 0. This terminology we have already used, but now we are going to a little more detail. That is the reason. So this is the first stationary series that we are going to learn, the simplest of all, which is known as the white noise process. So how this is defined? Its expectation is 0. The variance is a constant. Both are free from time. And these xt's are uncorrelated. So when I say uncorrelated, its covariance function is going to be something like this. That the covariant function is gamma x t plus h is equal to sigma square whenever h equal to 0, and is 0 whenever h not equal to 0. So whenever h not equal to 0 means whenever there is a lag, the autocovariance is 0. Whenever it is same to itself, it is the variance, because when h equal to 0, we know that this is variance. Now this process is stationary. When I say stationary, it means I'm bothered about the weak stationarity. So this process is stationary. Thus, a white noise is a stationary time series with mean 0 and a constant variance. Now you can see that this, I'm not talking about the distributions of xt, because we are worried about in the weak stationarity, we are concerned about the mean variance and the covariances. So only three conditions are required. But if you have a distribution who is completely specified, or whose distribution is completely specified by these moments, then we can say that the weak stationarity is actually can be same, or the definition of weak stationarity can be the same as that of the strict stationarity. So in addition to these conditions, if we assume that xt's are normal, we can see that these are strictly stationary as well, because now that we have joint distribution, any component that you take, it will have any particular subset that you take and move at a distance of h units on towards left or towards right, then you can see that they have joint normal distribution. Of course, in this case, they are uncorrelated, so they are independent, because in the case of normal, uncorrelatedness is same as independent. Now, such a process, we call it as a white noise. So this plays the same role of errors in a regression. So in regression, we write y equal to beta x plus epsilon. So here, most of the processes are written like this. So for example, we write like, so xt equal to some g x1 some theta plus zt, where this zt is white noise. So the meaning of this is uncorrelated. So zt is a weakly stationary series. Because its mean is 0, variance is constant, and the covariance is a function of time difference. So let's go back. So this is what the white noise. One question that you can ask: why white noise? Why not pink noise or red noise? Well, I am leaving that question to be. I mean, you find out the answer for this. Why we call such a process or such a series as white noise? I can give you a hint that when a white light passes through a spectrum, what happens to that? If you can find out the answer and how this is different from other colored light, so then we can get the answer to this. So what happens that in the case of other colors, the frequencies are going to be different, whereas in the case of white light, the frequency remain the constant, or the spectrum, when it passes through the spectrum, uh, it has a equal frequency. So it's basically this is the reason. Of course, you can find out more detail about that why we call white noise. But of course, the name is not very important. What you can see that it's like zero mean constant variance uncorrelated process. So if you have a sample simulated from a white noise, it look like this. So this is somewhat very close to the IID kind of setup. So now, how does it covariance and I mean autocorrelation and partial autocorrelation should look like? Because we have seen that partial autocorrelation is there or autocorrelation is there only for h equal to 0. For all others, it is not significant. So you can see that this is 1 because that is h equal to 0, the lag is 0. And for all others, these are within these limits. That means none of these correlations are significant. Similarly, the partial autocorrelations also, because they are actually zero. Theoretically speaking, they are zero. But for a sample, when you estimate it from the data, it need not be identically zero, but it will be insignificant. So that's what happens in this case. All the SEF and PSEFs are zero, except the first one, which is for h equal to 0. So that is 1 and all others are 0. This is how a white noise process look like. So if you get a data and if you plot the ACF and PSEF and if you get something similar, then immediately you can conclude that that process is like a white noise, or that process can be approximated by a white noise process. Let's see some other process. Now, this I want to now slightly generalize. Can you have the stationarity? I'm sorry. Can you have the seasonality? Can still the process be stationary? Because what we have seen that uh, the trend and stationarity actually take the trend and seasonality take the stationarity away. That is what we have learned, because we are looking for trend and stationarity all the time. So here I have an example where it doesn't matter even if there is seasonality, still there is a possibility that the process is stationary. By stationary, what I mean is weakly stationary. I'm not bothered about the strict stationary. So I'm considering the weak stationarity. Let's look at this example. It's very interesting example. So let's say xt equal to a cos omega t plus b sin omega t, where a and b are independent random variable with mean 0 and variance 1. And then if you compute the expectation of xt and the variance of xt, with very easily you can show that expectation of x. I assume that a and b are independent, so expectation of xt is 0 and variance of xt is cos square omega t plus sin square omega t, which is 1. So you can see that expectation is 0, variance is 1. You can also compute the autocorrelation function of xt. We have seen a couple of examples of computing the autocorrelation function. It's nothing but the correlation between xt and xt plus h. So you can actually compute them. And then you see that the correlation between xt and xt plus h is cos omega h. So what does it indicate? The t is relevant. It only depends on the time difference. And the cos omega h is a well-defined quantity. So you can immediately say that this is a weakly stationary process because the autocovariance or autocorrelation is a function of the lag. So that's why this is weakly stationary. Well, you complete this. That's not a big problem because you can actually, it's something like this. You have to see what you need to do is that uh, so correlation between xt. So you can, this is just a notation. Should have written. So this is expected value because mean is 0. Now you can substitute a cos of plus. Now you can see that this into, you simplify this, you get this as, you simplify because you can can simplify it. Can simplify it by considering this a cos omega t plus b sin omega t, and sorry. So you can see that this is basically so you can see that this is the difference of time points, and that's why you can also see that this is cos omega h, and what you get. So it's stationary, and this is non-negative. So if you want to look at, because I already mentioned that this is seasonal, so how that seasonality still turned out to be weekly stationary. So I told you that we are not considering the distribution at every time point, but we are considering the expectation. So, and as well as the variance. I mean, so these are, there is some kind of a computation or aggregation is being done. So you can see that this is the process which a cos a sin omega t plus b. This is, of course, generated observation. About 100 observations are generated, assuming that A and B are some normal 0, 1 random variable independent. And then you computed this. So you can see that how the covariance look like. So sorry, how the process look like. It is seasonal. You see, its seasonality is very visible here. But still, we have proved in the previous slide that it is stationary. Now, I want to show you some of the real non-stationary series. One of the important non-stationary series. Of course, I have given you only the very simple one, which is just a white noise. Now, I am going to consider different types of non-stationary series. Not very, I mean, all the different types. We'll discuss one of them, which is very important, and it has got a lot of application. Look at this non-stationary series. This is nothing but US unemployed women's data series, which is from 1961 to 2002. And this is monthly series of unemployed women between 16 and 19 in the United States. So you can see that this goes up and then it come down. So this is strictly kind of a non-stationary series, because it's not moving around one particular value, because the expectation start computing this, you can see that the the covariance need not be a function of time difference. Of course, I have not shown you the data as such. This is just the time series plot. So looking at the time series plot itself, it may be possible to sort of judge that the covariance, the process is non-stationary. Another example is this. It's quite clear that this is non-stationary. This is like, because if you compute expectation of xt, that has to be same for all t. That's the first condition, and then the variance and the covariance, which is a function of time difference. It cannot happen in this. Is a example of US tobacco data series 1871 to 9, and the same thing you can say. Now, what are these kind of process? Now, one kind of process which is very much useful, and a lot of application are there in the literature, is a process on uh, what we call it as random walk process. So what is this random walk process? It's a non-stationary. It's basically the partial sum of, you can remove this, and then it is nothing. If you assume mu equal to 0, this is nothing but summation I equal to 1 to t of zi. And zi, we assume that it is a white noise 0 6 square. And if mu is there, it has a drift. If mu is not there, it doesn't have a drift. So the drift, what I mean is something like this. See, for example, this starts here. It doesn't start at 0. So there is a drift here, which is this, and then the process starts from there. So that's what the drift means. So this is what the mean mu plus summation I equal to 1 to t zi. We can also write, because summation I equal to 1 to t minus 1 is xt minus 1 mu plus that. So you can also write xt equal to xt minus 1 plus zt. That's another representation. You can actually, this I am writing it without this mu, because if mu is not there, up to t minus 1 is xt minus 1. So that's how you write this. So this is called a random walk process. You are going to learn random walks in your stochastic process class. More about that. So I'm not, the random walk you might have seen, like you stand at a point and then toss a coin and decide whether you go to right or left. That's basically a discrete random walk. Now here what happens that zt, if I assume it is a continuous random variables, because our processes are mostly, we have agreed that we will be discussing a continuous random variable, and maybe you are going to show there that the random walk is actually tends to a kind of Gaussian process, course with some conditions, or Brownian motion rather. So you can also see that you can approximate it arch time, where it's like you are actually tossing a coin and then decide going to the right or going to the left. Now you can actually approximate it by considering at a time point, given time point t, where you are going to be. That's what, if you're starting at some point here, so that's what you are actually adding at each toss. You're basically adding this I equal to, then at time point t, where you are going to be. So these many tosses you will then. Now this process, here mu is known as the drift parameter. So this process has expectation mu, variance sigma square t. Obviously, this process is not stationary. The reason being that you can immediately see that the expectation is zero because this has mean zero, or the expectation is mu if you consider this format. This format, the expectation is zero. And the variance, you can see that for such a sum, the variance is each of them is sigma square, and therefore the variance of this is t times sigma square. So once the t is coming in the mean and variance, of course not in the mean, in the variance, this is no more stationary. Okay, so this is no more stationary, but it is very easy. I mean, like what you may think that that's not a big deal. If I divide the variance xt by square root of t, this will vanish. So why not consider that process? So let's see what happens in such a case. So one can define a new process yt as xt divided by square root of t and assume mu equal to 0. Mu equal to 0, just for the convenience, mu is not anyway not creating any problem, as mu is not a function of time. So the now if I divide by square root of t, you can see that the variance is also going to be sigma square, which is free from t. But then don't jump to the conclusion that it is weakly stationary, because mean and variance are okay, but what about the covariance? Is the covariance is a function of time difference? So what you should have when you actually compute the covariance, you should get so it's something like this. So you should get, say for example, if you are computing the rho t plus h, this should be a function of h only. Then only we will get, so which means that it is a function of lag. Otherwise, you can't, as once it starts depending on t, then you don't have the stationarity. We are talking about weak stationarity. I told you that we always talk about weak stationarity. So this fact is very clear that it is not going to happen in this case. Of course, you have to verify. So what is required? The process that I am talking about, you need to compute. So for example, this process which I have. So you can actually take this as 1 to t minus 1. Oh, sorry, this zt. You can compute this as xt equal to xt minus 1 plus zt. Uh, See this representation, we can actually write it as xt is summation xt minus 1, xt is equal to xt minus 1 plus zt. So this is actually random walk process. So in this case, of course, this one can write this as summation I equal to c zt minus. See, if you keep on substituting, what is this quantity? If xt is like this, then xt minus 1 is xt minus 1, xt minus 2 plus zt minus 1. So you get zt and zt minus 1, etc. You can now see that 1 to t minus 1 said I can go, and then going to be zt. So you'll be able to write like this. So essentially what I'm trying to say that this is a partial sum of white noise process that actually, that leads to a kind of non-stationary. Now, I did not prove that. Actually, I'm leaving that to you. You need to compute the covariance, because proof is based on whether the covariance or the autocovariance or the autocorrelation is a function of time difference only. So that you need to prove this actually. Okay, I'm just claiming directly. So I think you will be able to do that exercise, because it is find the covariance between xt h and show that it starts depends on t h t, or depends on t also. So if this is true, then this is correct. This is not happen in this particular case. That's what you are trying to establish. Okay. Okay, let's go further. So what is the behavior of this process? If you look at this behavior of this process, it doesn't have the mean reversion. So we can see that. So I'll show you with some examples. Say for example, see this particular process. It doesn't come back. Mean reversion means it has to be moving around somewhere in the middle. So somewhere in the middle of the process. I mean, like some point it should be moving around. Of course, we consider it as zero expected, because expectation of z equal to 0. If it is not, you can have a mu there, so should be moving around mu. That's what we are considering, but that's not happening. So this is why we can say that it is not weakly stationary. So for the time series plot of a random walk, there is no mean reversion. It doesn't come back to the mean. So the series seems to be just wandering off. See, for example, this is the random walk. This is with this a drift, because it's not starting at 0, so it's starting at some value here, and then it moves like this. Now we can see that if you have a random walk model, you can take the difference. So for example, if you have the random walk, it's xt equal to xt minus 1 plus zt. So for this xt series, if I define xt as xt minus xt minus 1, what is this yt is going to be? Yt is going to be zt. And zt is what? Zt is white noise. Therefore, yt is a stationary series. So a first order difference of a random walk is going to be stationary. So that's what it is here written. 1 minus b of xt is of a random walk. Consider 1 minus b of a random walk, which is this. So it is a white noise process. So the first order difference of a random walk is a stationary white noise. So here how I have shown you how how you can achieve the stationarity by a first order difference from a random walk. So this is a random walk process, and you take the first order difference, then it will be like, okay. So now one of the applications of this initial application, the first, of course, there are a lot of applications of random walk, but one of the initial applications of this is basically uh, in the context of asset return. So in the context of asset returns, we have seen what is meant by a return of corresponding to the price of a stock or a particular asset, and then the return corresponding to that we have defined in lecture. So here we can see that this random walk has a lot of application in stock prices. Some observation that you can make. So a random walk model has a widely seen as a statistical model for the movement of log stock prices. So is PT is the log of PT, uppercase PT, where this uppercase PT is nothing but this is the price of a particular stock, and this is the log of that. Now you can one of the model that you can approximate with this is PT equal to PT minus 1 ZT. So I mean ZT is like we may assume right now we haven't assumed any particular distribution. We simply said that it is a white noise. Okay, but you can still assume a particular distribution this, and then this can be a proper, I mean an approximate model for the stock return. But then people realize this is how initially people started, or researchers started modeling the stock prices is because what is happening because of the non-stationarity, we realize that this stock price is not predictable or not mean reverting because it doesn't come back. So how can you say what is the expected value? The expected value is keep on changing at every time point. So you can't really say that. So mean reversion doesn't happen. And one way of another interpreting, so people try to interpret this in a different way. If SETI has a symmetric distribution around zero, then you can say that it will be with a probability half, it goes to the positive side, and with a probability half, it goes to the negative side. So you can see that the price, the stock price from yesterday, it increases or decreases, okay, with a half probability each. So there is a 50-50 chance to go up or down, implying that PT would go up or down at random, and the chance of going up and down is 50. This is another model where, see, I haven't really assumed what is ZT. I'm just telling you, if you assume ZT as a symmetric random variable, maybe this is a kind of an interpretation. From previous days, you are actually increasing or decreasing. So that's what this kind of a model basically. Now, in the there is one particular terminology here which I haven't really explained. I skipped that, but maybe I can just mention you. So, for example, uh, so because I need to actually introduce AR model, but that time we'll have more discussion about that. But however, I can tell you what is happening. So, an AR1 model is something like this. Our AR1 model. And if I take this phi equal to 1, you get this as a random walk. So this is NAR1 and phi equal to 1 is the random walk. So what is the peculiarity? I mean, so great about this because this AR1 model, if for absolute of phi less than 1, we haven't proved, but I'm going to prove it a little later. We can see that this is AR1 is stationary. So phi equal to 1 is actually a kind of boundary case. So what is the meaning of absolute of phi less than 1? You have a unit circle, and in the unit circle you are trying to, for all the values of phi less than 1. So if your phi is equal to 1, so on the unit circle you have a problem, and that we have seen also. If you remember, our variance of an AR1 was nothing but sigma square upon 1 minus phi square, and this is defined only for absolute phi less than 1. So you don't have the weak stationarity beyond this. That means if it is on the boundary or it is above that, it doesn't happen. Phi, okay. Now this phi you can also link to a polynomial. For example, if I start writing the polynomial as 1 minus, so if I start writing this as an equation like this, phi z as 1 minus z, z into phi. So what basically this is coming from? So okay, because you may wonder what is happening. So I'll just write like this: phi b xt is equal to 1 minus b xt. So this is nothing but xt minus phi b 1. Okay, this is xt minus phi xt minus. So your process is this. This is the polynomial that you get from this equation. So what we are trying to say that if you are trying to say that you have this is to be because you will be in a position to write 1 minus phi b into xt equal to zt. So I want to now talk about this is xt minus 1. I want to talk about can you get this xt to be stationary in this case? So what essentially happens here is something like this. This so if for example if I now consider xt as 1 minus p equals zt. Now this is the xt expression. So what is happening here This is like you are actually considering an infinite linear combination of zt minus 1, zt minus 2. Because what is this going to be? This is going to be 1 plus 5b minus 5 square b square, etc. I mean, something like this. So what happened? Each of the b basically bring you, sorry, this is all plus. So each of them brings plus, etc. So essentially what you will have is, you will get something like 5 to the power of j z t minus j, for j equal to, so, uh, so this line. So 5 to the power of j, isn't it? I mean, this is if phi equal to 0, this is zt. So that you get the first term. Phi equal to 1, you have phi into zt minus 1, phi square into zt minus 2, etc. So what happened? You can see that this process or this series converge only if this absolute of phi less than. Now, this is not a deterministic series, it's a random series. So, when you have a random series, the convergence is discussed in terms of expectation. So, I'll make these things a little more rigor when we discuss the autoregressive model. Okay, so essentially, what we are trying to say here is, in a random walk is a particular random walk is basically a boundary case of an AR1 process. So boundary case where it become non-stationary. So you are that's what happened in this particular case. So this has a lot of application in financial series. Why we consider now, one question that the other day one of the students asked me, why we are considering returns instead of prices. Now return is log pt upon pt minus 1. That's what the return is. So the reason for that is, the return is just a single number which represents the investment or the scale free summary of the investment opportunity. Not only that, returns sometimes have good statistical property as compared to the price. So this claim I want to show you with a graph. In actual data, the stock prices of Z Entertainment Television Company in the National Stock Exchange. So 2 years data. So I have about 492 points daily data. So 492 time points are there. And if you consider this is the time series plot, so you can see that it is quite non-stationary. The time series plot for about 492 time points, stock prices. But if you consider, a first order, I mean returns, not difference, return. Return is nothing but log pt upon pt minus 1. So if you consider that, you can see that this is much more stationary as compared to that. So this is one of the reason that most of the time in a financial context we work with returns rather than the prices itself. So the adequacy of random walk model for market indices is questionable, because of the negative log price is very rare if it happens at all. Because the price is, when the price is smaller, log PT is turning out to be negative. So there is some, I mean, people may not be very happy with such kind of modeling. So, in fact, any past shocks in PT does not decay over the time. Consequently, the series has strong memory. That's what I was telling you, that this kind of a process has strong memory. Memory in the sense that the autocorrelation function, you can see that it doesn't vanish. For most of the stationary series, you can see that autocorrelation function vanish after some time, or immediately vanish in a geometric manner or an exponential rate. Whereas in this case, it doesn't vanish, which means that it memorized what had happened long back. So that's one reason. In economics, the shocks are said to have permanent effect. So if you give a shock and that has a long-term effect, then we call such as long memory. So the strong memory of the unit true time series can be seen from the ACF of random walk, and that's so I have now generated about 200 observations. This is a random walk, and you see the ACF of that. This red color is the model ACF, that means theoretical ACF. You can see all of them are one, whereas this green color is the sample data ACF. You can see that all of them are significant, even up to lag 40. So this is, you can't say that they are zero. So they are not coming down to zero even after up to. So this is the peculiarity of a non-stationary series. So this is of course a particular type of non-stationary series where we call it as random walk. Okay, thank you. So we'll stop this.